Hello everybody, today I'll give lecture on neighboring group participation. Okay, so neighboring group participation is mostly involved in classical, non-classical carbocations. So I'll just say what is the neighboring group participation. Okay, if a second molecular functional group which has an unshared pair of electrons or a double bond is present in the substrate molecule, it may participate in the substitution reactions. So the participation of nucleophilic substitution in a molecule in the substitution reactions at another point in the same molecule is known as neighboring group participation. So I'll write down here, if a functional group which has an unshared pair of electrons or a double bond is present in the substrate molecule, in the starting material molecule, in the substrate molecule, it may participate in the substitution reactions. So substitution reaction. Okay. So I'm repeating again. If a second functioning group which has unshared pair of electrons or double bond is present in the substrate molecule, it may participate in the substitution reactions. The involvement of nucleophilic substitution in the molecule in the substitution reactions at another point in the same molecule, at another point in the same molecule is known as neighboring group participation. Okay, group participation. So the substitution reaction takes place in the same molecule, having a nucleophile in the molecule. So for example, say, I'll write down, okay, I'm repeating again. If a functioning group which has an unshared pair of electrons or double bond is present in the substrate molecule, it may participate in the substitution reactions. The involvement of nucleophilic substitution in a molecule in the substitution reaction at another point in the same molecule is known as neighboring group participation. So I'll write down in this case point how it takes place. Okay, so a nucleophile can have acting as a, suppose cyclic compounds in a saturated system, we can have L is the leaving group, so X is the molecule having a lone pair electron, is a substrate. So it is a functioning group, second functioning group is a lone pair electron, and L is the leaving group. So you can have, so like this, so you can attack this participant in the like this, so you can go this way. Okay, leaving group script like this, so we got an intermediate. So this way X like this is positive charge now here, becomes positive charge here, like this. Okay, so we have a intermediate A here, let's say A. So you can now attack by nucleophile in two systems. Nucleophile having negative charge, nucleophile. Now it can attack either here or here in this tower. These two systems. So you can have plus L negative charge. Okay. So you can have two products. If we attack here, then go like this. Then we can have C nucleophile here attacks in this point. Okay, go this way. Then we have X here. So we have one product. If nucleophile attack here, then goes this way. Then we can have another product. Nucleophile attack here, and C and X here. Okay, so you have another product. So depending on the nature of the attacks by the nucleophile on the intermediate A, then we can have two products. So here, I'm repeating again, the second functioning group is having a lone pair electrons, unshared pair electrons. They attack to the, can participate in the substitution reactions, acting as a substitution reactions. It attacks to the carbon atom and they clip to form an intermediate, which can be attacked by a nucleophile in two ways. Okay, so we can do different products. So here participation by the neighboring group takes place. Now another molecules, say double bond here. Let's say we have another one having double bond here. So let's say X. So Y is double bond. Then we have substitution. L is the leaving group. Then we can have here. So it can double bond also can participate in the substrate in second functioning groups having double bond here. So here also same case, attack here and clip is L. So we can have intermediate C and then X, then Y here, Y. Okay. So now Y is become positive charge here. Okay. So this is we have another intermediate. Let's say B plus L negative charge. Leaving group. So now nucleophile can attack in two ways. Earlier case here, like similar cases, nucleophile can attack in two ways here also. Nucleophile can attack either in this side or this side. Then you can have different types of product. So if you attack, let's say this attack here, then you go like this. So you can have same product. So we got X double bond Y. Okay. Nucleophile attack here. Then you can have, if we attack here, same case, you can go like this. Then we can have another product. So nucleophile attack here, then you can have another product, X double bond Y. So here, so you attack this way, this double bond here. So this is here I'm speaking about again. Okay, so here participation takes place by the first case in the case of lone pair electrons. For the second functioning group attacks participate in the nucleophile reactions to give here. And here in the second case, double bond participate in the second functioning group will participate in the substitution reaction. So I am giving these two cases. Okay. Now let us come to evidence for existence of these neighboring group participations. So participation evidence for the existence of neighboring group participation. Evidence for the existence of neighboring group participation. Neighboring group participation. So let's say it is evidence how this participation of neighboring group takes place. Participation. Okay. So what is the evidence here? So this mostly evidence of this neighboring participation can be explained mostly by solubilisis of compounds. Then we can say whether there is a neighboring group participation takes place or not. So for this case, let's say two examples. So let us have suppose for examples. Okay, so solubilisis of or histolysis of two compounds. The first one is, so we have this one OTS living group, and then we have, okay, this is OS acetate group. Okay, and second one is this transistor, and then we have cis. Okay, cis you can have cis OTS and cis OSC acetate group. So here, when solubilization takes place by the acetate group, acetate acetic acid, using acetic acid, same case, acetate anion and acetic acid. So the first case is a trans system. You can say trans 1, 2, 2 isotoxy cyclohexyl paratorium sulfonate. You can say like that. Or you can say trans 2 1, 2. Okay, 2 isotoxy cyclohexyl. This is paratorium sulfonate. Okay. OTS paratorium sulfonate. Toluene sulfonate. Okay, this is trans system. Here is cis. So now you can say cis isomer. Cis 2S1 2 isotoxy cyclohexyl paratorium sulfonate. OTS is there. So this is cis. Okay. When you solubilize takes place, or you can say acetylysis, this trans will give trans. So intentional configuration takes place here. In the case of here, you can take trans will give trans diacetate form. Okay, diacetate compounds. So they have cis will give cis with again inversional configuration takes place here. So here OSC and then here OSC. Okay. So I'm repeating again that in the case of acetylysis of trans 2 isotoxy cyclohexyl paratorium sulfonate, we got trans diacetate. This trans, okay, what are trans diacetate. Here also trans, okay. So here in this case retention of configuration takes place. Here in the second case inversion of configuration takes place. So this how this forms trans will give trans and cis will give trans can be explained by participation of this existence of this neighboring group participation. So let's see the mechanism how this neighboring group participation takes place. So let's see the mechanism of the formation of this compound. Let's say examples here, let's say from trans systems. Okay, let's say trans. Okay, this is a OTS living group, and we have this trans OSC trans system or C double bond or OSC. Okay, see that. So we have trans system here, trans isomer. So first, in the presence of this will attack here, living group will go. So in the attack from front side, so we get a front side. So we got here front side. So living group minus OTS as a living group paratorium sulfonate. This is the living group. So we got this. So here O, then here CO, C. You can write C, and CH3 here. Then you have CO participate here. Okay. So here now it becomes this C becomes positive charge because it linked to this one and leaving this one. So we got this another intermediate. Okay, this intermediate can undergo isonicity like this. So it can give this one will give or this one will give. So we can have this one. I can write this way here. C, and so we can have O here and double bond here, the O here, and then C. Okay, C3. You can see, okay. So it becomes positive charge here. So yeah, oxonium ion got. Similarly, from this side, if you take this side, then you can have here. You can write another from here. Same case, you can write O, and here O, and come over here, C3 here. Okay, it takes from this side, so it becomes positive charge. So oxonium ion here. So you got this one. So depending on these two, we got because it's intermediate. Okay, now attacked by this acetate ion, and so I see. So now you can attack from the back side. So you attack from the back side, so you can have another. So you attack from the back side, attack from back side. So because in the front, you can attack from the front because of this two bulky groups are here. So you can attack from the back side. So now you come this way. Or you can attack. Let's say attack from the back side here. Back side, attack from the back side. So it comes this way. Now you can have this broken down, this one. So you can have, let's say this one, OSC. So you can O, C3, C1O, then you come from the back side attacks. So it becomes OSC. So you can attack from this side also, you can attack from the back side. Attack from here. So you can go this way. Then you can get similarly here. OSC will come here and the OSC will come here. So we can have two taps. So there are diacetate. So this is diacetate. So you get a trans one, trans system. So trans give trans isomer, trans diacetate, the product. So I'm giving here participation. So in this case, participation of the lone pair electrons from the substrate, nucleophile substrate takes place. So this is showing how this mechanism shows that participation of neighboring group takes place. So neighboring group participation takes place in these reactions. So I'm repeating again that for two compounds we have cis and trans. Okay, one is a trans 2 acetoxy cyclohexyl peratol sulfonate, and the one is cis 2 acetoxy cyclohexyl peratol sulfonate. When they undergo acetylysis or solubilisis with acetic acid, you're going to got trans will give trans isomer and transport down diacetate, and cis will give trans diacetate also. So here in the case of trans will give trans product, there is retention confusion takes place, but in the case of cis isomer will give trans diacetate. This here inversion of confusion takes place. So I'm giving here mechanisms. In the case of trans is that here. So now you take from the participation takes place like this. This participation by double bond here takes place. So we got a confusion like this. Here, so in a neighboring group, this is a group attack. You can attack this way also, no problem. Here you can attack this way also, and then we can have similar case here will come. Okay. This will attack here, then they will give, suppose I'm writing here, okay, then I lone pair electron can take place here also. So here another mechanism, this one OTS, living groove, and then this is the OC double bond O CH3. So here you can take lone pair electrons, so can participate in neighboring groups like this, and here this is another intermediate. So here got this, attack from front side, attack from front side, okay, front side attack, because back side is blocked by the living group OTS, front side attack. So you got, this is O, then here C, double bond C3, so O becomes positive side here, okay. So you attack like this, so you get this one product. Then you get another one, you can have this one, and then you can finally cytolysis will give the same product. So you can have this C, is same as C. So it is another mechanism how it is formed, okay, C form. So this shows that participation of neighboring group takes place. Neighboring group participation takes place because there is a lone pair electrons, double bond can take place. So now let's see there are many tips how this participation can take place by many groups. So we can have CC participation, single bond or double bond like that. So participation by various groups. Participation by various groups, or so like so you can show by like first one is CC double bond participation, or you can say CC double bond neighboring groups, double bond participation. You can have different types of participation, and then CC the single bond participation, and then we can cyclopropyl ring participation, and for one aromatic rings participation like this. So participation or neighboring groups can take place by different groups such as CC double bond, and then CC single bond, and then cyclopropyl ring participation, and finally the aromatic rings participation. So let's discuss by one. First one is a participation by of CC double bond. So we can have one example. We can compare these two examples. Okay, here OTS hydrogen here, OTS living group, oxalic groups, double bond here. Another one no double bond here. Another one there, this we can say electron sufficient. Another one electron deficient. Non-classic carbocation. Okay, this is A and B. Okay, here A is much faster than around compared to. So here association of this resistance takes place. Then double bond can participate this way, living groups. So here A participation, pi bond participation takes place here. Is a cytolysis of A. So I can write down cytolysis of A or sorbolysis of A takes place much faster than takes place faster than about 10 to the 4, 11 times, very fast. Okay, about 10 to the faster. Then there are sorbolysis of B. Okay, so here D to the part. This shows that participation of CC double bond takes place. So yeah, I'm giving one example. Okay, so CC double bond participation takes place, and in the case of cytolysis is about 10 to the 11 times faster than the B. So I'm giving example here. So here double bond CC double bond participation takes place. Next we can have CC single bond participation. Okay, second one is CC single bond, because a neighboring group CC single bond neighboring group participation takes place. So this can be also examples by earlier in the non-classical carbocations. I've given how carbocations, non-classical carbocations are formed. So we can have many cases I have already given in the non-classical carbocation types. In OBS, this one, norbornine, 2 norbornine, brosylate. Okay, brosylate. This one is, you can say this is exo 2 norbornine brosylate. Can so like earlier we have shown in the case of non-classical carbocation. So here you can just lost this one, can make carbocation here, then again delocalization by sigma bond, and again double bond here. So we have shown earlier. Okay, so you can have this one. Okay, so you can have this system. So this is non-classical carbocation. So now acetyl ionic can attack two ways. Can take this one. YSC cytolysis can take place. But either this I can attack here. You can attack either here, this system, or here, or here. Okay. So I can write this form also like this. Okay. So this is a non-classical carbocation. So you can have sigma bonds are formed here. So here you can, I will write down here. Okay. OSC. Yeah. So you can take this way, another one can take this way. Okay, there are two possible positions are there. So the non-classical carbocation here, you migrate this one. First you click this one, then you put the charge here. I told earlier, and then you can take here. Then another one, click this one, and then the localization takes place by single bond. Single bond takes place. So put the charge here. So you can take here. So if you take from here, you got this product that is exo acetate. Okay, so like this. If we take this one from here, then we can have this one. Okay, this OSC here attack from this side, the one positive charge here. So this can be equivalent to this side. Okay, so you got an exo product OSC. So XO, these are all XO gases, they are same molecules. So this is the how single bond CC bond participation takes place in a nitrogen group. So here positive charge blows this one, positive charge, and then this way single bond participation takes place like this, or it takes this way. So these are another examples for formation of single bond participation. And then third one we have MicroProfile group participation, MicroProfile participation. Okay. Third one is MicroProfile ring participation. MicroProfile ring participation. Okay. So here also in the bridgehead compound, okay, you can have examples. Let's say the examples. This one compare with this MicroProfile here. Then you can have this living group, also phenyl, then hydrogen here. Another system we can compare this. There is no substituent here. OCO, phenyl, living group. Then we can have another double bond unsaturation there. Then same living group. Then we can have another one MicroProfile here. You can compare this MicroProfile, but the system living group is this side, hydrogen here, or phenyl. Okay. So we can say 1, 2, 3 numbering like this for compounds. So here MicroProfile participation takes place. So here thrombolysis, histolysis of this one is faster than this greater than thrombolysis 1, greater than the 3, and then 4 order of thrombolysis like this 4, and finally second is this. It doesn't have any double bond or MicroProfile. Actually, MicroProfile rings are acting as a double bond properties. MicroProfile rings have double bond property. Nearly MicroProfile rings have double bond properties. Okay, similar like double bond, behave like a double bond participation takes place. Double bond like properties. Okay, they're similar with they have. Okay, so they can be very stable. These compounds are very stable. So here double bond here, so it can go this way. And so here I am showing the MicroProfile participation. I will give some examples here. One is most rate of thrombolysis faster than other cases. So here also I will give one example here. So let's see how MicroProfile participation takes place in this case. Okay. So here, so like this coagulation participation takes place like this. So the MicroProfile participation takes place. So there are rare cases that we can have these living groups. So here we can have this positive, there's a log link, this one broken down, so it becomes positive charge, and like this. Then again this can, the link is broken down here, then you can have another one, carbocations. So you can have another one, link this one, and you can put this here. So and then this way we can write many systems, okay, like earlier cases. So here MicroProfile ring participation takes place. Finally, last one we have aromatic ring participations. Aromatic ring also can take place. Group neighboring group participation. So aromatic ring participations. So I am giving examples here how aromatic rings are undergo participations. So let's say compound and substitution reactions. Let's say this one living group. And then we have, let's say R1. And this one, let's say R2 here. Then we have phenyl groups here, aromatic ring. Okay, and then we can have this one. Okay, now this the participation takes by double bond participation takes place like this, and living group is going like this. Then we have minus X negative charge, so we can have the C. This is then phenyl groups here. Here you can have, so here R1 and R2. Okay, so this link to a positive charge here. Then we have this going to delocalize this way. then we can have R1, and then this R2, and then like earlier cases we have discussed this in the non-classical carbocation also. Okay, so here we have the bond here. Similarly, you can have this way. So we have a this way, so on. Okay, so this way, many are there. So in hybrid form, we can write this way. That is this C, here better. So here carbon can write non-classical carbocation. We put the charge here, and then we have R1, and then R2, then here. Okay, so when thrombolysis takes by Y, the nucleophile attacks, then we can have different two types of one. So when I write on the products, you can attack like this way, or another that one. Okay, you can have two types of products. Y can attack, nucleophile can attack here or here. So we can write out the products here. So here aromatic participation takes place as a neighboring groups. So we can have C, so R1, and this is R2, then R2, and attack this is substituents are here, so phenyl groups. Yeah, okay. And then here Y attack from this side, so it goes this way. So Y attack here. Another products, if Y attack this side, then again this way. So rotation takes place, and then here C. So here rotation will come to this one. Here phenyl groups here. And so now it comes to Y attacks here, and then we have this one and this one, and then we have phenyl groups here. So now Y attacks this side. Okay, this side attacks. So now it goes this way. So here phenyl goes this way, and then we have R1 and then R2. Okay. So we've got two types of products. So here rearrangement takes place. So R1, R2 rearrangement at C1, and then here retention at C2 takes place like this. So this is about the participation of aromatic rings takes place. So this is today we discussed this about the participation of neighboring group participation. So these are classes today we have wind up. So we can take next class we can have reactions and rearrangements of carbon ions. Okay, thank you.